Hey everyone, and welcome back to the channel. Today, we're talking about something every serious Linux user or developer eventually deals with: compiling and installing system-level programs from scratch. Compiling GCC in the power of ld_library_path. Part 1. Why compile? Getting started. As someone who does a bit of programming, I install C compilers pretty often. Of course, Python is also a great tool, but at the end of the day, system-level programs are usually written in assembly, C, or C++. When we look at what systems need, we often talk about runtimes: Java runtime, Python runtime, or .NET runtime. Interestingly, there's no such thing as a C++ runtime that we need to install separately. Linux systems are largely spearheaded by the GNU open source organization, and the super important GCC compiler project, led by GNU, is truly considered a system-level program. But we can go even closer to the core, right? We have things like libc. This is part of the LDD package, and you can find its project on GNU. Right now, the project version is at 2.42, but my current computer is running 2.39. Generally, Linux doesn't recommend that you compile these core, close to the kernel packages yourself. For example, the crucial glibc.so.6 file is located in lib x86-64 Linux GNU. If you mess with this library for even a second, the system immediately loses the ability to handle file structures. You won't be able to use cd to change directories, or even ls to list files. Everything will fail. So, changing system-level programs like this requires serious consideration. I've had the painful experience of finally completing the compile, only for the system to crash because the modification method was too risky. When you can't even see where the files are, you can't do anything. Part 2. Compiling GCC v14. So, today, I'm going to install a newer version of GCC. My system is fresh, and the current version is 13.3. I checked Ubuntu's site, and since my system is Ubuntu 24, it basically supports version 13, and it can install version 14. I tried to download the v14 package before, but I couldn't find that specific version. Therefore, my upgrade path is to recompile it from the source code. The Ubuntu documentation says the latest version is GCC 15. Here's a key feature of GCC. This version's compiler needs to be compiled by the previous latest version's compiler. So, if I want to update, I must go to v14 first, not jump straight to v15. I opened Ubuntu's official support version page, and in the Code tab, it listed where to download the source code. The total download size is quite large, so I first checked the new site to see what prerequisite libraries I needed to build. It looks like quite a few, but generally, the installation instructions are similar for every version. Even though these are for version 15, I'll fulfill all these requirements first. Then, if configure needs anything else, I'll add it. The first package I checked for was patch using apt-list installed. Next up was Sphinx. The one after that was a bit more unique. Many of my colleagues are heavy TeX users. TeX's unique writing method lets you create special mathematical expressions, like square roots, fractions, and exponents. Plus, it can turn the compiled document into a PDF file. I searched for installation advice, and besides the TeX language itself, it recommended TextStudio and TextMaker. After installing them, I followed the advice and created the simplest possible PDF file to check. Looks like it works correctly. I then installed the rest of the necessary packages one by one. Part 3. The compile process. Now, back to the GCC download. It's finished. Let's decompress it. I want to introduce a feature here. GCC has an automatic download function. I've noticed that open source code for programs closer to the Linux kernel often provides this kind of automatic download procedure. It's located in the contrib folder. The file is called download_prerequisites.sh, and you need to run it in the source code's root directory. Before compiling, we must run configure to adapt it to my computer's environment. Next, we prepare for the actual compilation. I created a separate build directory outside the source code. This is the method basically recommended by the project development team. I moved into that directory and started the configuration. The GCC official website lists a lot of tunable parameters. Since it's so detailed, I tend to get confused. So I actually look at other people's tutorials to see which parameters they used. Basically, since I might compile RISC-V programs or assembly programs, I want to install every compiler GCC provides. So, I didn't set any specific programming languages in the parameters. No setting means install everything. Another parameter to pay attention to is prefix. As a longtime Windows user, I used to think it just added a few characters to the file name. But from the tutorials, I learned that for new, it directly specifies the target installation directory. I also set the program_suffix parameter to append the program's version number to the compiled executable's name. If you're missing anything, the configure process will stop and prompt you to supply the necessary items. Since I had already found all the dependencies and downloaded the prerequisites, configure successfully wrote a makefile for us. The next step is to run make. GCC is a massive project, so I'll pause the video here and continue recording once the compile is finished. Part 4, Installation and the variable of the day. Welcome to the second part of the video. It took me about 6 hours to finish the compile. The compile creates executables in the configure and make steps. The files were mostly stored in the current working directory. If you search diligently, you can find the completed files. However, there is one more step. Make install. This tells the compiler to install the compiled program in the location you specified. Because I compiled system-level code, I had to use the system administrator sudo command. After make install finished, I listed the files in the new directory. It looks like quite a lot. C++, GCC, AR, Alto, and others. I also listed where the system's currently used executables are located. They are still in the usr bin directory, which has a huge number of files. So, I need to specify the file I want to see. Let's look for GCC. The system found 4 files: GCC, GCCAR, GCCNM, and GCCRanlib. And they all look like links. For example, GCC is the executable that users usually call. It's a symbolic link from GCC 13. And GCC 13 is a symbolic link from x86-64 Linux GNU GCC. In the directory we just built, we have GCC 14 and also x86-64 PC Linux GNU GCC 14. They are not linked. They are 2 separate executable files. They should theoretically be the same file. Linux's link command, if it's not a symbolic link, might completely copy the source file. Therefore, we don't need to link the newly built GCC 14 to its other x86 program. Instead, we directly replace the link on the system to point to the GCC 14 we just compiled. I'll use this method to replace all the new executables with the newly compiled versions. Then, I'll continue compiling GCC v15. The safe way to swap libraries. Directly replacing the system's executable link is one method. But, as I mentioned before, some system functions absolutely cannot disappear. like when you're renaming or overwriting them. The moment you change the functionality of, say, the underlying supporting library for the copy command, the copy command breaks instantly, whether the new version is successful or not. If you have a way to make it swap and execute immediately, there might be a chance to recover. But if the new program hasn't been tested and it turns out to be broken, well, that's a mistake you'll regret forever. This is where I introduce our global variable of the day, ld_library_path. This variable is basically the same concept as Windows environment variables. It tells the Linux system where to look for libraries. Think of your Linux system like a massive toolshed. When you run an application, it often needs to grab some common tools. Those are your shared libraries. Files ending in .sob. Normally, your system knows where to look for these tools in standard spots like lib or usr lib. But what if you compiled a custom tool? Or you're testing a newer version of a library that lives in a non-standard directory? That's where ld_library_path comes in. What is ld_library_path? ld_library_path is an environment variable used by the dynamic linker loader ld.sob in Linux and other Unix-like systems. At runtime, when you execute a program, it's a separated list of directories that the system searches for shared libraries before looking in the standard directories. It's a powerful but temporary fix, mainly used for testing, running custom compiled software, or when the libraries are not installed system-wide. Important security note, because it overrides standard paths. Using ld_library_path globally, e.g., in your basher, is discouraged because it can lead to security risks and instability if you accidentally load an incompatible or malicious library. Use it for specific applications or temporary testing. How to use it. Examples. The core command to set this variable is export. Example 1. Setting it temporarily. Let's say your custom library, libmymath.sob, is in home user custom_libs. You can set the path just for your current terminal session. Bash. Number 1. Check the current value. It might be empty. Number 2. Set the path temporarily. Number 3. Run your program. Number 4. When you close the terminal, the variable is unset. Example 2. Appending to the existing path. Recommended. What if you need to add your custom path but don't want to erase any existing paths already set in ld_library_path? You must append your new directory. Bash. Append your new directory to the existing path. R. If you want your custom path to be searched first. More common for testing. Example 3. Setting it for a single command. This is the safest and best practice when you only need the variable for one specific program. Run. You set the environment variable right before the command. Bash. ld_library_path is only set for this specific execution. The variable is automatically unset once the my_application_binary finishes executing. That's your quick crash course on ld_library_path. It's an indispensable tool in a developer's kit, but remember to use it wisely and sparingly. You might find this video on creating symbolic links for libraries helpful for context. How to create symbolic links for libraries. ld_library_path. Alright, that's it for this video. I'll catch you next time.